All right, we have here problem number 1 from the equilibrium worksheet, forces in 2 dimensions. Excuse me. In this problem, we are given a sign hanging from a wire and supported by a rigid bar. The rigid bar is 1.5 meters long, and the wire is 4 meters long. Now, one of the common questions is, how do these distances then, these lengths, relate to the forces that are acting in this system? And the answer is they really don't, other than the fact that they dictate the angles at which those forces act. So we have a known angle here, and we can actually calculate this angle here. We know that this bar is perpendicular to the wall. So we have a 90-degree triangle. We can do trigonometry to figure out the angles at which these forces are acting. We're going to draw a free body diagram using the point at which all the forces act. All the forces act at this point where the bar is pushing on the wire is holding up the sign, and it's connected to the wall. So that is going to be our dot for the free body diagram. Now we have 3 forces acting there. We have the weight of the sign. Obviously, weight is acting straight down, always acts straight down. And that is equal to the mass of the sign, 25 kilograms, times the acceleration due to gravity, 9.8 meters per second squared. I put a negative in there just to kind of keep track that that's actually going down. You can choose to put that negative in now or later. And we have a tension that is supporting this sign. That tension comes from the wire. Since this is a wire, it's only able to pull, and so it's pulling upward at whatever angle we are going to figure out here. We'll call it theta for now. And then we have a third force, a force from the bar, and we have to ask ourselves, is this force acting to the right, or to the left? And if you sort of inspect what we have as a free body diagram right now, we have a force that's acting downward, straight downward, and a force that's acting sort of up and to the left. Well, those 2 forces cannot balance each other out. And if you have a third force that acts to the right, then we can have a balanced system. If this force of the bar was acting to the left, it would not be able to maintain equilibrium. That force would not be able to maintain equilibrium. So that is not the way it's working. So we have a free body diagram that looks like this. Now, how do we get this angle? Well, that is what we are going to calculate from these lengths of the wire and of the bar. So we know that this 1.5 meters is adjacent to this angle, and this 4 meters is the hypotenuse of this triangle that's made over here. So the cosine of that angle theta must be equal to the adjacent 1.5 meters over the hypotenuse 4.0 meters. That means the inverse of that inverse cosine is going to equal theta, which I calculate as 67.9756 degrees. And for simpleness sake, let's go ahead and call that 68 degrees. Now let's go back to our free body diagram and sort of inspect it a little bit. We know that this object is in equilibrium because it's not moving. So therefore, the sum of the forces in the x direction has to equal 0, and the sum of the forces in the y direction has to equal 0. Well, we have a force here in the y direction, Fg, and a force here in the x direction, F bar. But then we have a force that's in neither dimension 100%. The tension in the wire. Okay. So maybe we'll call this Tx, and we'll call this Ty. Now, inspecting that, you can sort of see that if you add the force in the bar to Tx, they're equal and opposite, so that will be 0, and Ty needs to be equal and opposite from Fg. Well, we don't know any numbers except for Fg, so let's calculate Fg. Fg is 25 times negative 9.8. And I calculate that to be 245, or negative 245 newtons. Now, looking at this, we need to sort of say, okay, well, Fg plus Ty must be 0. Therefore, 0 must be equal to negative 245 plus Ty. And that's the mathematical way for saying that Ty has to be a positive 245 newtons. Well, now you know a side, 245 newtons, and an angle of 68 degrees. And you can calculate everything else on this triangle. So we can say Tx then must be equal to 245 newtons over tangent of 68. Now, to get at that, we would have to say tangent of 68, tangent of 68 is equal to opposite 245 over adjacent Tx. Okay? And remember, these two things can switch places in one of these equations. So that's how we get Tx as 245 divided by the tangent of 68. And that gives me a force of 98.986 newtons, or 98.99, which is close to 99 newtons. And I guess technically that's a negative 99 newtons since it's pointing to the left. Now, again, you can say the same thing as we did here with Fy, some of the forces in the y direction. We can say the same thing for some of the forces in the x direction. That Tx must be, or plus F bar must be equal to 0. So that a negative 99 plus whatever F bar would be would have to be 0. Well, that clearly makes F bar equal to 99 newtons. Tx is also 99 newtons. Well, now it's easy to get T. So T must then be equal to the square root of 245 squared plus 99 squared. And I get 264.24 newtons. We'll call it 264 to make life easy. And there we have it. We have calculated the force in the bar is exerting and the force that the wire is exerting. From not a whole lot of information, from just the 25 kilograms mass and knowing the directions of that the forces are acting.